Okay, what we have here is a capacitor with two circular plates. And what we can do with this capacitor is slide the plates so that we can vary the separation between them. I've attached a power supply to the capacitor and I've charged up the two plates now. And what I'm going to do is disconnect the power supply. And so the capacitor is charged, so one plate will have a charge of plus Q on it, the other plate a charge of minus Q, and there's some voltage V across the capacitor. I've now connected a high impedance voltmeter across the capacitor, and we're reading a voltage here. Looks like about 20 volts right now. What I'm going to do now is take the plates and increase the separation. And let's watch the reading on the voltmeter. We see how it goes up. It's almost pegged now. And if I push the plates back in, the voltage decreases. Okay, so with the fixed charge on our capacitor, if I increase the plate separation, the voltage drop across the capacitor goes up, and as we decrease the plate separation, the voltage drop across the capacitor decreases. Here's the situation with the fixed charge on our capacitor plates. The electric field intensity will be determined by the charge density on the capacitor plates. And the voltage drop will be the electric field intensity times our plate separation D. Now if we take the right plate and start pulling it so as to increase the plate separation, the extent of the electric field intensity lines will still be from the positive to the negative charges. So with the increase in D, there's an increase in voltage across our capacitor. So when you're pulling the right plate away from the left plate, you're doing work. It takes work to do that, and that's showing up as the increase in the voltage drop across the capacitor. Now if we let go of the right plate and let it be pulled towards the left plate, the capacitor is actually doing work. And that work then shows up as a decrease in the voltage as the plate separation D is decreasing.